And now for a calculus trick. So the following is something I call major-minor, or the major-minor rule. And it's basically a shortcut to do something called U substitution. And we'll learn U substitution in our section on techniques of integration. However, this is a nice shortcut to do a U substitution without getting too formal about it. And it will help us to solve or compute some slightly more complicated integrals. And recall that when you compute an antiderivative, or when you compute an integral, the whole idea is to figure out what function, when you differentiate it, gives you the function you're looking at. So what this does is kind of undoes the chain rule. So we can look at an example. Suppose we have y is equal to sine of x squared. Well, the derivative is going to be cosine of x squared and then times 2x. Right? So here we have our inside function u of x, and on the outside we have u prime of x, just like that. So the major-minor rule basically deconstructs this and helps you reverse it. So if you have something like the integral of cosine of x squared times x, which is essentially this derivative right here, except you're missing the 2, you should be able to integrate this just based on what you know about taking derivatives. And so the whole idea of the rule is that we call this part the major part. So this is where you have something that looks like you would need to use the chain rule if you were to differentiate it. Right? So it's cosine of x squared. You know if you differentiate that, you're going to need the chain rule, and the inside function is the x squared. And then the minor part is always going to be up to a constant multiple, the derivative of the inside function. So the minor part is right here. So major, minor. And the whole idea is that you just reverse the steps of differentiation. So the derivative of sine is cosine. So the integral of cosine is going to be sine. So what you do when you do major and minor is you integrate the outer function. So cosine becomes sine. So it's sine of x squared. The minor, this is the fun part, he just gets to hang around for the ride. So the minor is just copied without any action whatsoever. And then you divide by the derivative of the inside function. So the inside function was x squared. So instead of multiplying by the derivative of x squared, we're going to divide by the derivative of the inside function, which is the derivative of x squared. The derivative of x squared is 2x. So I'm dividing by the derivative of the inside instead of multiplying by the derivative of the inside. And also I'm engaging my integration rule backwards. So the derivative of cosine is minus sine, but the integral of cosine is plus sine. So I did the rule backwards. So cosine becomes sine. So cosine of x squared becomes sine of x squared. The minor stays along for the ride, and then I divide by the derivative of the inside. Now the only way this works is if when you divide by the derivative of the inside, that cancels out with the minor, except possibly some constant multiples. So aside from constant multiples, the derivative of the inside, when you divide it, has to cancel with the minor. So we see that the integral of cosine of x squared times x, well, the x stays along for the ride. It just ends up right here. Cosine becomes sine because the integral of cosine is sine. So cosine of x squared turns into sine of x squared. And then we divide by the derivative of the inside. So we divide by the 2x. And it only works if you can cancel out all of the functional dependency on x. So the constants are okay. This 2 out here is okay. But this x has to be canceled out with the minor. So everything in the minor has to cancel with when you divide by the inside, and all the x's when you divide of the derivative of the inside have to cancel out with the minor. So the minor and the derivative of x have to basically cancel out perfectly, except for an additive constant. So this is going, and of course we need plus c. So this is sine of x squared over 2 plus c. Now we can check, well, what's the derivative of sine of x squared over 2? Well, d by dx of sine of x squared over 2, well, derivative of sine is cosine, so it's cosine of x squared over 2 times the derivative of the inside, so times the 2x. and notice the 2's cancel, and we're just left with x cosine of x squared, which is what we're trying to integrate. So sine of x squared over 2 is indeed the antiderivative for x cosine of x squared. So it works exactly like that. So I have a number of examples prepared, and we'll see how this major-minor method works in each case. So it's kind of a nifty rule, and I hope you see exactly what's going on. We're literally just undoing the chain rule, and we'll do this slightly more formally in our chapter on techniques of integration when we introduce U substitution. So that's a little bit of a formalism around this rule. But this is just the basic rule itself, and in my own experience, I've seen students who kind of struggle with U substitution sometimes because it's a little bit more abstract. But this is a straightforward rule where, okay, the minor's here, the minor is essentially the derivative of the inside, and then we divide by the derivative of the inside, and they have to cancel each other out. And you see that it's just an undo of the chain rule. So let's do a few other examples. So if we want to integrate x e to the x squared dx. Okay, well the major is going to be right there, e to the x squared, that's the complicated piece. And you notice that with the major, it's a function that if you take the derivative of, you need to use the chain rule. And so we also want to identify the inside function of the major. The inside function of the major is x squared. Now the derivative of x squared, essentially, when I say essentially, I mean up to a multiplicative constant. So the derivative of x squared is essentially x. It's actually 2x, but I'm not worried about that extra constant of that extra factor of 2. So the derivative of x squared is essentially x. So the x is our minor, right? So we see that essentially the derivative of x squared is right outside, and then that's just the derivative of the inside function. So when I integrate this, it's equal to, okay, the major, so how would I integrate e to the x? Well, to integrate e to the x, you just rewrite it. So the major is e to the something, so we do e to the x squared. The minor is just copied, so it just, nothing happens whatsoever to the minor. And then we divide by the derivative of the exponent. So normally when I take the derivative of e to the x squared, I would multiply by the derivative of the exponent. Since I'm integrating, I divide by the derivative of the exponent. So the derivative of the exponent is 2x, so I divide by 2x. And now this won't work unless the x that I divide by cancels out with the minor. So the minor and this x cancel out, and of course I need plus c. So the whole antiderivative is e to the x squared over 2, and then plus c. Check it out. Take the derivative of this. E to the x squared over 2, the derivative is going to be e to the x squared times 2x. Now the 2's cancel out, and we just get x e to the x squared. So the derivative of this guy is exactly x e to the x squared. And that's how the major-minor method works. Let's hit up another example. So suppose we have the integral of x squared sine of x cubed. Well, the major is the big part, and the major itself has an inside function, which is x cubed. Now, the derivative of x cubed is essentially x squared. It's actually 3x squared, but when I say it's essentially x squared, I mean it's a constant times x squared. So the derivative of the inside function x cubed is essentially right here. So this we call the minor. So this whole integral is going to equal, the minor gets carried along for the ride, so we just get x squared. The integral of sine is negative cosine, so we get minus cosine of x cubed, and then we divide by the derivative of the inside. The inside function is x cubed, so we need to divide by 3x squared. And it only works if the x squared that we're dividing by cancels out with the minor. So all the x's in the minor function have to cancel out with all the x's of the derivative of the inside. So this x squared cancels with that x squared, and we just have a negative cosine of x cubed over 3 plus c. So we can see that this checks out because the derivative of negative cosine is sine, right? Derivative of cosine is minus sine, so if I have a minus right here, derivative of negative cosine becomes plus sine. Then we multiply by the 3x squared, which is the derivative of the inside. The 3's cancel, and we're just left with x squared sine of x cubed. So this is indeed the correct antiderivative. Our next one gets a little bit more interesting. Suppose we have the integral of cosine of x e to the sine of x. So first we need to identify our major and minor. So right here we see a function of a function. So the inside function right here is sine of x. And the derivative of sine of x is essentially cosine of x. So this will be our major part. And then the cosine of x, which is always essentially the derivative of the inside function. So the major part has an inside function, which is sine of x. The derivative of sine is cosine. Right? If I differentiate e to the sine of x, I'm going to end up with a factor of cosine, which is where my minor came from. So this is now going to equal, okay, the minor gets carried along, so we get cosine of x. Now the major, when I integrate e to the x, I get e to the x, so I get e to the sine of x. And now I divide by the exponent, so the derivative of the exponent is cosine of x, so I divide by cosine of x. And again, it only works if the cosines cancel. So basically the antiderivative is e to the sine of x plus c. And then you can check that, that works. The derivative of e to the sine of x is e to the sine of x times the derivative of a sine, which is cosine. So this is exactly the derivative of this one. Let's do another one. So here we have the integral of sine squared x cosine of x. So what we have here is the major and the minor. So remember, sine squared of x is basically sine of x to the power 2. So the function is really x squared. And then the inside function is sine of x. So the inside function is the sine of x. The derivative of sine is cosine. So the derivative of the inside is right there. It's the minor function. And then we have something squared. So when we integrate this, so the minor just comes down. So we have cosine of x. Now when we integrate sine of x squared, this is something to the power 2. So it becomes something to the power 3 and then divided by 3. But then we also have to divide by the derivative of the inside. So the derivative of the inside is, well, the inside function is sine of x. So the derivative of that is cosine of x. So we divide by the cosine. And it only works if that function of x cancels out with the minor. So we have sine cubed x over 3 plus c. And again, it makes perfect sense. Sine cubed of x, to differentiate that, the 3 comes down and changes to a 2. So when this 3 comes down, it cancels with the 3 in the basement. So we get sine squared x times the derivative of the inside, which is cosine. So the derivative of sine cubed x over 3 is exactly sine squared x cosine of x, and it all checks out. Let's see an example where it doesn't work. How about the integral of e to the x squared? Well, if you just go about this and say, okay, well, it's e to the x squared divided by the derivative of the exponent divided by 2x plus c, that does not work. This is wrong. Right? So that's a big no-no. And the reason is because when I divide it by the derivative of the inside, that x in the basement here doesn't have anything to cancel with. Right? And if you actually go and try to take the derivative of e to the x squared over 2x, you don't get e to the x squared. You get e to the x squared plus another term. Because here we have to use the product rule, or the quotient rule if you prefer, to compute the derivative of this. And when you do that, you get an extra term. Where you can use major minor is with x, e to the x squared. So in this case, the major is e to the x squared, and the minor is the x. Now the inside function of the major is x squared, and the derivative of the inside is essentially right here. It's essentially x. It's actually 2 times x, but it's essentially the same thing up to a constant multiple. So when I integrate this one, well, I rewrite since it's an exponential function, e to the x, the integral would be e to the x, so e to the x squared, divided by the exponent, 2x, and then the minor gets carried along for the ride. And in this case, the x's do cancel, And so I'm just left with e to the x squared over 2 plus c. And you can check this is the antiderivative of x e to the x squared. Because if I take the derivative of e to the x squared over 2, well, it's an exponential, I rewrite it, and then I multiply by the derivative of the exponent. So taking the derivatives, I multiply by the derivative of the inside. The 2's cancel, and I'm just left with x e to the x squared, which is what I'm integrating right here. So that's exactly how the major-minor method works. And we'll formulate this more precisely again when we talk about use substitution. But for right now, I mean, really, you're a detective, and it's like a crime scene, because when you're computing an integral, you have to think to yourself, what function can I come up with that when I take its derivative, I'm left with x e to the x squared. So this is just a technique to help you think backwards. How do you know it's true? Because when you get to the answer and you take its derivative, it's the right derivative. So it's basically putting on your detective cap, working backwards, and trying to figure out what function, when you differentiate it, gives you x e to the x squared, or whatever it is you're trying to integrate.